In this class, we're going to have a look at the first important test that will allow us to determine whether certain series are convergent or divergent. And it is called the integral test because it will involve integrals. In fact, if you think about it, a series is the limit of a sum, right? It's obtained as the limit as k goes to infinity from 1 to k of the sum from 1 to k of the terms of a sequence. Well, but so is an integral, or at least a definite integral, right? We defined a definite integral, a Riemann integral, as also the limit as n goes to infinity as the sum from 1 to n of certain things. Now, in both cases, we have limits of sums which become infinitely large. In one case, in the case of the series, we're adding more and more terms, which we keep adding on. In the case of an integral, we are actually adding more and more elements, but each time we're actually changing them by changing the thickness of the delta x's. But in both cases, we're constructing a sum which is becoming bigger and bigger and bigger. So there must be some connection, right? Yes, there is, in fact. And this connection is the first connection which tells you that series are not really a separate topic, something on their own, but they are very much connected to integrals and to calculus in general. So let's see how this test works. Now, so what we're going to do is we're going to assume a few things. So this test will only work under certain specific situations. Thank goodness those situations occur quite often in when we're looking at specific series that we're interested in. So what are these conditions? The conditions, first of all, we start from a function, regular function, which is positive, decreasing, and integrable on the interval from 1 to infinity. Now, this limitation of 1 is not really, it's a bit of a fake limitation, because by shifting everything I'm going to tell you from now on, you can make that function start anywhere you want. So it could start at 2 or 3 or 4 or whatever. But the important thing is that we have a function that from some point on is going to be positive, decreasing, and integrable. From this function, what we can do is we can construct the corresponding sequence. So we're going to figure out what the values of this function are at n equal 1, 2, 3, 4, etc. And that allows us to construct a sequence. And of course, what we're going to do is we're going to look now at the series that is obtained from this sequence. Now, what happens in this case? If this is true, then for any integer k, and for the sake of illustration here, the k I'm going to use is 7. Okay, so we're going to prove all these things from 1 to 7, but of course that doesn't matter, it's just a visual illustration. It turns out that for any integer k, what we can do is we can do the following. First of all, we can look at the integral from 2 to k of our function. So that will represent the area under the curve from 2 to 7. Okay, well, if we look actually at these spatial rectangles, which are a little bit above the curve, what are they? Well, the area of the first rectangle, the one between 2 and 3, has base 1 and height equal to a2, right? The next one also has base 1 and the height is going to be a3, and so on up to a6. So what we see in here is that the integral, the area under the curve, is going to be less than or equal than the sum from 2 to 6, which will be k minus 1, of the numbers an, right? The area of each one of those rectangles is going to be exactly a2, a3, a4, a5, a6. Well, for good measure, what we're going to do is we're going to throw in one other rectangle. So we're going to look at the other rectangle that would correspond to a7. Okay, so what we can say is that the integral from 2 to k is going to be less than or equal to the sum from 2 to k of those an. Of course, I've added something else on the right hand side, so I've made it even bigger. Now, what I'm going to do is I'm going to take all these 6 slices, 6 or k minus 1 in general, and I'm going to shift them all 1 unit to the left. Okay, so I'm going to push everything to the left. So I'm dealing with exactly the same rectangles, only I'm seeing them a little bit shifted to the left. But now what I can do is I can observe that these rectangles all together form an area which is going to be less than or equal to the integral from 1 to k. Remember, my k was 7 of f of x. Remember, that integral is going to be given by the area under the curve, and this one is still going to be bigger. And I'm going to do one last step. What I'm going to do is I'm going to look at the terms of my series, A1, A2, etc. But starting this time exactly at A1. Notice that the sum I had used so far started at A2. So A1 now is going to be the big rectangle all going all the way to A1. And then the second one is back to my A2, A3, A4 up to A6. And so what I can say is that the area under the curve from 1 to k is going to be less than or equal to the sum from 1 to k minus 1. Remember, now I'm stopping at 6 because I'm dealing with just 6 slices, right? K minus 1 slices. All right, so I have this series of inequalities which are basically linking together in some kind of inextricable way the series and the integral. Okay, so let's look at this set of inequalities, and let's see what happens when we're going to let k go to infinity. Well, the integral from 2 to k becomes the integral from 2 to infinity of f of x dx. The sum from 2 to k becomes the sum from 2 to infinity. The integral from 1 to k, of course, becomes the integral from 1 to infinity. Of course, all those inequalities are going to remain because they are true for every k, and therefore they're going to be true in the limit. All right, well, what does that mean? I mean, what do these inequalities now between the series and the integral mean? Well, as a consequence, what we can say is that the series and the integral will both diverge or both converge. Because let's say that the integral diverges, okay? So that means that the left-hand side integral, the integral from 2 to infinity of f of x dx goes to infinity. Remember, our function is positive, so the only way for this thing to diverge is if it goes to infinity. Well, but if it does, that means that the sum from 2 to infinity of our series is also going to infinity because it's bigger than it, right? So it's going to diverge. On the other hand, if the integral converges, then the integral from 1 to infinity of f of x, the third integral, the third piece of our inequality, that's going to go to some finite number. And that means that our series, which is going to be less than it, also is going to have to go to some finite number, and therefore it's going to have to converge. So the destiny, the fate of both the series and the integral are inextricably linked. But not only that, notice that these inequalities not only tell us about whether they converge or diverge, they also provide us an approximation to each other in case they do converge. So this integral not only tells us if our series converges, but if it does converge, it gives us a way of approximating it. Notice that the first two inequalities tell us that the value of the series from 2 to infinity is going to be somewhere between the integral from 2 to infinity and the integral from 1 to infinity, and we can use that as an approximation.